Dear students, last time we discussed integral domains and characteristic of a ring and other topics. Today we will first of all we start with proving that we have proved that a finite integral domain is a field. Today we will prove that if P is a prime, then ZP integers modulo P is a field. Before proving that, let's note a property of prime numbers. Let's consider an example. Consider prime 7. We note that seven divides 126, and you can see that, and 126 can be written as 21 multiplied by 6. So 7 divides 21 multiplied by 6. Note that 7 divides 21. Again, let's choose another prime, say 11. This is a prime in Z. We note that 11 divides, let's say 88, and 88 can be written as 22 multiplied by 4, 4 multiplied by 22. So 11 divides 4 multiplied by 22. Note that 11 divides 22. So in fact what we have noted is that if a prime divides product of two integers, then that prime divides one of them, one of maybe both, but at least one of them. So we have noted that if P is a prime, if P belongs to Z is a prime, and P divides product of two integers A and P, then P divides A or P divides B. P must divide one of these two, A or B. So this is what we are going to note. An element P belong to Z is called prime if for a B belonging to Z, P divides product of A and B implies that P divides A or P divides B. In fact, we can define prime in general setting as well, but for the time being, we just note this particular property of a prime. So let's come to the proposition we are going to prove, and the proposition says that if P is a prime, then ZP, integers modulo P, that is 0, 1, 2, so on up to P minus 1. This contains P elements. Then ZP is a field. Note that we have proved that a finite integral domain is a field. We will use this particular proposition in order to prove that ZP is a field. So for proof, first of all, we note that ZP is finite. We note that ZP is finite because ZP contains P elements. Secondly, we note that ZP is commutative ring with identity. Further, ZP is commutative ring with identity, with multiplicative identity, anyway with identity. We have to prove that ZP is a finite integral domain. So ZP is finite, ZP is commutative ring with identity. All we have to prove is that ZP does not contain zero devices. Then it will become integral domain and finite integral domain, so it will be a field. So we only have to prove that ZP does not contain zero devices. So we only have to prove establish that हम सिर्फ ये प्रूव करेंगे कि ZP ज़ीरो डिवाइसेस ZP में ज़ीरो डिवाइसेस नहीं है, that ZP does not contain zero devices. In order to prove that ZP does not contain zero devices, we take two elements A and B so that P divides their product. It means that we take two elements or two integers A and B so that their product is zero. Let me write it. Let AB belong to Z so that their product AB is equal to 0, means their product is congruent with 0 mod P. Suppose this is the case. Then you know that what does this mean? This means that P divides product of A and B. This is what congruence is. Interpret when we say in terms of dividing the integers. So then P divides product of A and B, but P is prime. Therefore, as we have seen previously, therefore P divides A or P divides B, and therefore now if P divides A, then A is congruent with 0 mod P, or A is equal to 0. A is congruent with 0 mod P, or if P divides B, then B is congruent with 0 mod P. So we have proved that if product of A and B is 0, then either A is equal to 0 or B is equal to 0. And therefore, last time I told you that in order to see that a ring is integral domain, this is what we do. We see that if product of two elements is 0, then one of them becomes 0. If this happens, then that ring becomes integral domain. 0, that commutative ring becomes integral domain. 0 divisors do not exist in that particular ring, and therefore ZP is an integral domain. So let's conclude that we have noted that ZP is finite, ZP is commutative ring with identity, and ZP does not contain 0 divisors. This sums up that ZP is an integral domain. Now ZP is finite and ZP is an integral domain, therefore ZP is a finite integral domain. Therefore, ZP is a finite integral domain. But every finite integral domain is a field. Every finite integral domain is a field. Therefore, ZP is a field. So this completes the proof. Let's just note this thing. What we are saying is that a finite integral domain is a field. For example, Z5, Z7, Z11, Z13, all these are finite and all these are integral domains. So these are integral domains. These are integral domains, and are finite. Each one of these is finite. Therefore, each one of these is field. You can check it by yourself. Note that Z is an integral domain. Is an integral domain, but is not a field. Z is an integral domain but is not a field. Why? The reason is very simple, because Z is not finite. Z is infinite. So what our result says, that a finite integral domain is a field. Z P, if P is prime, is finite integral domain, so this is field. Similarly, Z5, Z11, 7, Z11, Z13, these are finite integral domains and are each one of these is field. So having said that, Let's come to an other topic. As we have studied, we know that when we talk about sets, we talk about subsets. When we talk about groups, we talk about subgroups. Now we are discussing rings, so we come to the concept of subring. Subring. A subgroup is subset of the group which is group under induced binary operation. Under induced operations, in fact, what I should say. And similarly, a subring, let me define it properly. Let R be a ring. Then a subset S of R is called subring. Is called subring of R if S is ring under binary operations. Let's call under operations induced from R. So under same operations, whatever are in R, S must be a ring. What we mean is as follows. Let R be a ring. Then a subset S of R is subring of R if following are the conditions. If, first of all, S must be closed under addition and multiplication. What it means is that A plus B belong to S. For all AB belonging to S, S must be closed under addition. Secondly, A multiplied with B belong to S. For all AB belonging to S. And then number 3, 0 must belong to S. That is additive identity must belong to S. And then number 4, additive inverse of every element must belong to S for all A belonging to S. So these are the conditions for a subset of a ring to be a subring. Let's see examples. You can very easily see that Z is subring of or the ring of real numbers. Let me write here reals. Similarly, Q rationals is subring of or the ring of reals. Similarly, or the ring of reals is subring of C, the ring of complex numbers, complexes, complex numbers, in fact, complex numbers. So these are Z is subring of R, Q is subring of R is subring of C, and you can see that Z is also subring of C. Q is subring of C. You can conclude these things on your own. Consider this ring. Consider Z, the ring of integers, -3, -2, -1, 0, 1, 2, 3, and so on. Anyway, consider 2 times Z. 2 times Z. This is -6, -4, -2, 0, 2, 4, 6, and so on. We know that 2Z is a ring. You can see it very easily. We know that 2Z is a ring as well. So 2Z is subring of Z. Is subring of Z. Just note one particular thing, that the ring Z contains multiplicative identity. But 2Z is a subring of Z, but it does not contain multiplicative identity. So if a ring contains multiplicative identity, its subring may or may not contain multiplicative identity. But if a ring is commutative, then its subring is also commutative, because commutativity is just inherited. So let's make note of these things. Note. A subring, if ring R is commutative, if ring R is commutative, then its subring S is also commutative. But if a ring R is a ring with identity, if a ring R is a ring with identity, with multiplicative identity, then its subring S may or may not, may or may not contain identity. Multiplicative identity, in fact, may not contain identity. And you have seen this thing in our previous examples. You can also note that, further note that, 3Z, 4Z, 5Z, so on, are subrings of Z, and none of these subrings contain multiplicative identity. Now let's come to another very important concept, and that is of ideal of a ring. Ideals. In fact, when we discuss ideals, we discuss left ideals, right ideals, and two-sided ideals. Two-sided ideals. Let's define definition. First of all, we define left ideal. Let R be a commutative. Let R be a ring, not necessarily commutative. Let R be a ring. Then ideals are sub-rings in fact. Then let R be a ring, then a sub-ring. We denote it by I. Then a sub-ring I of R is called left ideal. We are going to define left ideal is called left ideal of R if there is only one condition, and that condition says that if we take an element of the ring R, this is the element of the ring R, and we take an element of this particular subring I, suppose that element is X. So R is element of the ring, X is element of the subring. We multiply these two with each other because both are elements of the ring R, so can be multiplied. So Rx, this should belong to the ideal I, the subring I, and this is for all R belonging to R and X belonging to I. देखिए हम इसे कहते हैं लेफ्ट आइडियल। वजह यह है कि हम रिंग के एलिमेंट्स के साथ सब रिंग के एलिमेंट्स को लेफ्ट हैंड साइड से मल्टीप्लाई करते हैं, यानी रिंग के एलिमेंट्स लेफ्ट हैंड साइड पर हैं। इसी तरह से हम राइट आइडियल डिफाइन करते हैं। सो लेट्स सी व्हाट द डेफिनेशन ऑफ राइट आइडियल। लेट आर बी अ रिंग, then a subring I of R is called right ideal, और आपको अंदाज़ा होगा कि हमने क्या लिखना है। इस कॉल्ड राइट आइडियल ऑफ आर इफ़, अब हम सिर्फ इतना करेंगे कि एक एलिमेंट रिंग का लेंगे, एक एलिमेंट सब रिंग का लेंगे, लेकिन रिंग के एलिमेंट को हम राइट हैंड साइड पर लिखेंगे। सब रिंग का एलिमेंट लेफ्ट हैंड साइड पर, रिंग का एलिमेंट राइट हैंड साइड पर। एक्स आर बिलोंग टू आई फॉर ऑल आर बिलोंगिंग टू आर and x belonging to I. So this is definition of right ideal. Next we come to definition of two-sided ideal, और आप बड़ी आसानी से अंदाज़ा कर सकते हैं टू साइडेड आइडियल में, टू साइडेड आइडियल की डेफिनेशन में ये कंडीशन भी होल्ड करेगी और ये कंडीशन भी होल्ड करेगी। सो लेट्स डिफाइन दैट। लेट आर बी अ रिंग, then a subring I of R is called two-sided ideal, is called two-sided ideal of R if कंडीशन का आपको अंदाज़ा है क्या होगी इस केस में। कंडीशन में रिंग के एलिमेंट को लेफ्ट हैंड साइड से मल्टीप्लाई करें और सब रिंग के एलिमेंट को राइट हैंड साइड से, तो ये प्रोडक्ट भी आई में होना चाहिए। और आप रिंग के एलिमेंट को राइट हैंड साइड से मल्टीप्लाई करें सब रिंग के एलिमेंट के साथ, तो ये एलिमेंट भी आई में होना चाहिए। दिस अगेन फॉर ऑल R belonging to R and X belonging to I. So this is definition of left ideal. These are definitions of left ideal, right ideal, and two-sided ideal. Let's come to examples. First of all, let's see example for left ideal. So for this example, I may not be able to write everything, but you can check it on your own. In fact, we are going to consider rings of square matrices. The simplest we can take is a ring of square matrices of order 2 by 2, of order 3 by 3, of order 4 by 4, of order 5 by 5, of order n by n, n cross n. And I think best choice would be ring of matrices of order 3 by 3. Entries from set of real numbers. It will be easier for us in order to understand the example. So consider, let's write it M3. M3 is equal to a ring of matrices A11, A12, A13, A21, A22, A23, A31, A32, A33, such that, let me simply write A's are real numbers. Are real numbers. All these entries are real entries. So consider square matrices of order 3 by 3 with entries from set ring of real numbers or field of real numbers. This is A's. Let me write it now. Okay, I think it is A's. So these A's are real numbers. Then we know that M3 is ring. In fact, this is a ring with identity. Is ring with identity. And just to recall, and M3 is non-commutative ring. In fact, is non-commutative ring. Now, consider this particular subset of M3. So consider this particular subset. Let's call it I. This is subset of M3 whose say first two columns are first and second column, first or third column, whatever you like, or second or third columns are the first two columns are, anyway, it is your choice. First column is 0, second column is 0, and third column may be or may not be 0. So A13, A23, A33. Consider this such that A's are reals, A's are real numbers. So consider this particular subset of M3. This is subset of M3. First of all, you can see it very easily that this is an abelian group under addition. Just note that this I is a subring and you can check it very easily. So we know that we can easily check that. Closure under addition, closure under multiplication, you can see it will happen. So we can easily check that. I is subring of, this is subring of M3 and you can check it on your own. Let's see the property of being ideal. This is in fact left ideal. We know that for any, let's take an element of M3. Let's take it as B11, B12, B13, B21, B22, B23, B31, B32, B33. Let's take this element of M3. So for any element of M3, if we multiply this particular element of the ring, note that this element of the ring, B11, B12, B13, B21, B22, B23, B31, B32, B33, we multiply this particular element of the ring M3 with some element of this subring I. Let's take this as element. So first two columns are 0, then A13, A23, A33. You can easily note that this is equal to, when we will multiply this first row with first column, we will get 0 at this place. Then first row with second column, we will get 0 at this place. Then first row with third column, this may be a non-zero element. Let's call it C13. Then second row with first column, 0. Second row with second column, 0. Second row with third column, this may be non-zero, C23. Whatsoever the result is, similarly we get 0, 0, and let's call this non-zero element as C33. So this is equal to this particular element. This particular element is again of same type. So this belongs to I. So if we multiply an element of a ring from the left hand side with an element of this subring, result belongs to this particular subring. So therefore I is, this will happen with all such choices. Therefore this particular subring I is left ideal, because we are multiplying element of the ring from the left hand side with elements of the subring, is left ideal of M3, left ideal of M3. So let's come to another example. Again, consider M3, the same ring. Consider M3 as above, and consider, but in this case we are going to consider subset of M3. Let me write it with I again, because we do not have many symbols to represent our concepts. So consider I. Previously we took I the subring of those elements for which first two columns were 0. Now we take those matrices in which first two rows are 0, and third row may be 0, may not be 0. So A31, A32, A33, and let me write it. A's are real numbers. A's are real numbers. So having taken this is subset of, in fact this is subring of M3, as we have noted previously. You can easily verify that. You can easily verify that I is subring of M3. And further, now let's take an element of M3 and an element of I and multiply element of M3 with element of I from the right hand side, not from the left hand side. Further, for any, let's say use same symbols, B11, B12, B13, B21, B22, B23, B31, B32, B33 belonging to M3, we have. Now we take an element of I, 0, 0, 0, 0, 0, 0, A31, A32, A33, and multiply it with this element of the ring, that is B11, B12, B13, B21, B22, B23, B31, B32, B33. And you can easily see that when we multiply this row with this column, we will get 0, and then second row with circle. You can easily see that our result will be first two rows will be 0. You can check it on your own. And when we multiply this row with this column and write at third place, this will be a non-zero element. Let's write it as D11, D1, D31, and then again you can see this D32 and D33, and this particular element belongs to I. So therefore in this particular case, therefore that particular subring of M3 is right ideal, of M3. So we took these simple examples. In fact, note you can choose any ring of square matrices. Let's say Mn, where n is an integer, n belong to set of natural, not integer, where n belong to set of natural numbers. You can choose any ring of square matrices Mn where n is a natural number, and find left ideals and right ideals as above. You can take ring of square matrices of order 4 by 4, of order 5 by 5, of order 6 by 6, whatever. So like, so you can find a lot of examples of left ideals and right ideals. So this was about left ideals and right ideals. Let's have a very important observation.